Hello everyone, my name is Ana Ortega and I'm currently doing my master's degree at the University of Alberta under the supervision of Dr. Mirko van der Van. And today I'm going to talk about my research, the monitoring of hydraulic fractures using an integrated approach. We want to study hydraulic fractures propagation at temporal and spatial scales by analyzing low-frequency DAS, pumping information, and microseismicity of one hydraulic fracturing treatment. And we're going to compare these results with a numerical model. Different data types hold different information, and this integrated analysis could help identify completion issues, and so help in the design of more efficient unconventional reservoir completions. The objectives of this project are the interpretation of low-frequency dust strain fronts for one hydraulic fracturing treatment, to determine fracture network between the treated and monitoring wells, to compare the dust strain fronts with microseismicity and to a fracture model, and we want to do all this to gain insight in the relationship between strain changes, injection rates, microseismic events, and hydraulic fractures. The research project consists of three phases. The first phase of the project is the analysis of the low-frequency dust data and the pumping information. We are going to look at dust stream fronts, characteristics, and fracture characteristics like formation breakdown pressure, frac hits, propagation speed, and propagation direction. In the second phase, we are going to analyze the microseismic clouds to obtain their trajectory and length, and we are also going to compare microseismic events location and timing to the low-frequency dust data. For the final phase, we are going to use the PKN model to compare the previous results with this as a validation tool. This is the well's geometry of the site. The treated well is the blue line, and the monitoring well with the dust fiber is represented by the black line. The fracturing operation had 38 fracturing stages, represented by the blue circles. This fracturing treatment was open hole ball drop completion. Both wells are in the middle member of the mound information, and the separation between them is around 150 meters. Now, distributed acoustic sensing, or DAS for short, is a type of fiber optic sensor. These sensors use light to sense the information of the medium and can obtain a measurement at every point in the fiber, as the fiber is the sensor. The DAS interrogator unit works by sending light pulses into the fiber at constant intervals. Some of the light traveling in the fiber is reflected back to the interrogator unit where the phase is measured. Any vibroacoustic disturbance that affects the cable produces variations in the phase of this backscattered light. These phase variations in the return signal provide measurements of the strain the fiber cable is subjected to. This figure shows the hypothetical straining cable responses of a propagating hydraulic fracture. As the fracture approaches the monitoring well, the cable extends, and the extensional strain increases until the fracture hits the well. When this happens, the cable on the fracture is still extended, and there is a large extending strain increase centered at the point of interception, surrounded by compressing strain as the cable on both sides is being compressed due to the fracture opening. When the stimulation ends, the fracture starts closing, which causes the strain pattern to reverse almost immediately. This is an example of the low-frequency DAS response for one hydraulic fracture in one stage. The x-axis is time and the y-axis is measured depth. The port depths of the fracturing treatment are projected on the monitoring well on the left, represented by green triangles. We call them clusters in this study. The red dots on the left represent the fracture hits measured depth. For both triangles and dots, the filled ones correspond to the current stage and the unfilled ones to the other. In the strain fronts, the color red indicates extension while the blue indicates compression. The fracture signal resembles the shape of a dragonfly with a heart-shaped tip, and blue wings on the sides, who are also known as the stress shadow. Some dragonflies present an extending signal that shows almost at the start of the injection. We call them antennas. The zone where the strain pattern reverses is called relaxation zone, and the part of the dragonfly after the strain pattern reverses, we call it the tail. The strain front characteristics in the pink boxes were picked on every strain front as they give information about the number of fractures created during the stages and the restimulation of previous stages. For the dust and pumping analysis, we first picked the formation breakdown pressure represented by the blue line. It's at this pressure that the formation will break and will allow the fluids to circulate inside the rock. The formation breakdown pressure is the first peak of the bottom hole pressure curve it becomes continuous. Then we pick the frac hit time represented by the green line. It's at this time that the fracture intercepts the monitoring well. We identify the frac hit as the bottom of the heart-shaped tip of the dragonfly where the wings start. Next, we pick the frac hit measure depth, represented by the red circle on the left. This is the place in the cable where the fracture intercepted the monitoring well. To calculate the frac hit measure depth, we selected the top and bottom depths of the heart-shaped tip and calculated the mid-range between those two values. Using the frac hit measure depth, we determined the frac azimuth, which shows the propagation direction of the fracture. To do this, we plotted the frac hits measure depth on the monitoring well and connected them to their corresponding cluster with the line. Doing this for all stages creates the fracture connection map, which shows the fracture network between the wells. Next, we calculated the fracture propagation speed, assuming the fracture propagates perpendicular to the well. The separation between the treated well and the monitoring well is divided by the difference in time between the formation breakdown pressure and the frac hit, which we call the dust hit time. During the strain front analysis, we noticed some stages do not present the heart-shaped tip. They just have a line that appears shortly after the start of injection, which we call the antenna. The answer as to why this happens came from 3 stages where the same stage was restimulated after a first injection. For the reopening of the stages, the dragonflies don't present a heart-shaped tip. There is just the antennas. Knowing that a fracture had been opened previously at the same place, we concluded that the absence of the heart-shaped tip most probably means that the fracture was already there. Other stages present antennas, but they also have heart-shaped tips happening later, like in this stage. These antennas come from fractures from previous stages. We came to the conclusion that a previous fracture is being restimulated, but the injection did create a new fracture in this stage as well. Now I'm going to show the multi-stage results for this phase of the project. This is a graph with the dust characteristics distributions for all stages. Most of them present the expected heart-shaped tip. Most stages as well present some sort of antenna. And most stages present characteristics of having created multiple fractures, which will be that they present multiple heart-shaped tips, multiple wings, and/or multiple tails. This graph shows the fracture propagation speed taken from the dust strain fronts for all stages. Data with the speeds above 45 meters per minute were considered outliers and deleted. The average speed of fracture propagation in this well is 21.13 meters per minute, and we see how the speed increases in the later stages. This could be because the injection rate was increased systematically with stages. This is the final fracture connection map with original well geometry. The blue line is the treated well. The blue dots on it are the clusters for every stage. The black line is the monitoring well with the fiber. The red dots on it are the fracture hits, and the red lines are the fracture azimuths. Most of these fracture trajectories are compliant with what was expected. They propagate perpendicular from the treated well. However, there are some paths that have a steep inclination angle. This could be because there are other fractures in the formation that diverted the fracture, or something unexpected happened during injection. For the second phase of the project, we used microseismicity to analyze the hydraulic fractures. Hydraulic fracture stimulation is often accompanied by induced microseismic events resulting from the reactivation of pre-existing fractures or the creation of new ones. These microseismic events can help to monitor the propagation and geometry of hydraulic fractures by mapping their spatial and temporal pattern, as this information gives an indication of the rock volume affected by the simulation. Plotting microseismic events based on their time and location on their respective dust stream fronts can present a more complete interpretation of fracture development and propagation, and could also give us insight on the interaction between the strain patterns and the microseismicity. For this analysis, we first plotted the microseismic events in space with the wells to visualize the microseismic cloud. Then we added the linear regression of the microseismic cloud, which is the red line in this case. The linear regression gives an approximation of fracture trajectory according to the microseismic events. Next, we look at the length and depth of the microseismic cloud. The light blue dot is the treated well at the origin, and the black one is the monitoring well 150 meters apart from the treated well. This plot was used to calculate the microseismic cloud's length by measuring the distance from the treated well to the last event on the right. After that, we wanted to project the microseismicity onto the strain fronts. To do that, we first deleted all the events on the left side of the well and events that were too far away from the injection point. Then, we projected the events onto the monitoring well to obtain their measured depth. After obtaining the measured depth, we plot the microseismic events on top of the strain front as a function of the time of their occurrence. And this is an example of this type of analysis. Now I'm going to show the multi-stage results for this phase of the project. This plot shows the microseismicity clouds for all stages, and we can see how they mostly propagate towards the northeast, but we have some stages where they are propagating towards the southwest. Maybe the stress shadow is making the fractures to go in the opposite direction, or there is too much fluid already in that direction, so the fracture changing directions. This plot shows a schematic of the wells with pink lines that represent the fracture length according to the microseismic cloud. The fractures are placed in the position of the clusters, but don't take into consideration the angle of propagation. The microseismic lengths are longer in the early stages than in the later ones. Now, this is an example of the most common response for the analysis of the microseismic events on top of the strain fronts. The microseismicity usually concentrates on top of the dragonfly and happens continuously during the injection. Different behavior might mean that the fluid is going to other places or fracture communication. For the third phase of the project, we use the Pekin model as a diagnostic tool to see if things are going according to plan, because we want to understand why in some cases the different data types show different information or behavior. The Pekin model allows us to make a prediction on how the hydraulic fracture is growing over time. I decided to use the Pekin model because this model is suitable for long fractures with a smaller and constant height. This is the formula of the Pekin model to calculate the fracture half length, and the parameters for this model are plane strain modulus, injection rate, fluid viscosity, fracture height, and injection time. Some of these parameters are fixed values and don't change in all analyses, while others change depending on the stage. The Pekin model was programmed to first estimate the fracture half length at the end of the injection based on the injection time and parameters. This plot shows the fracture half length growth during the injection, and the fracture half length at the end of the injection is displayed. Then we use the Pekin model to estimate the fracture half length at the dust heat time. According to the strain fronts, it is at this time that the fracture intercepted the monitoring well, so we will expect that the fracture half length will be at the monitoring well at this time. If they are not, this will give us an indication that something unexpected happened in that stage. Next, we wanted to compare the microseismic cloud with the Pekin results and the frac azimuths obtained from the dust data. And to do this, we took the fracture half length given by the Pekin model and integrated it with the frac azimuths to create the Pekin fracture, which in this case is the green line. We plotted the Pekin fracture in a space with the wells, the microseismic cloud, and its linear regression. This plot helps visualize the similarity or difference in the angle of propagation and length between the DAS-FRAC azimuths, the Pekian results, and the microseismic cloud. We expect that if the fracture didn't change directions, the Pekian fracture and the microseismic cloud's linear regression will have a similar trajectory. Now I'm going to show the multi-stage results for this phase of the project. This plot shows the schematic of the wells with blue lines that represent the fracture half-length predicted by the Pekian model. The fractures are placed in the position of the clusters, and we can see how fractures are longer in the early stages than in later ones, and this is mostly because the time of injection is longer in these early stages. Then this plot shows the fracture half-lengths at the dust heat time, which are the orange lines. As mentioned before, the ideal situation will be that all these fracture lengths are at the monitoring well at this time. A range of good agreement has been placed at minus plus 50 meters of the monitoring well, represented by the dotted blue lines. Most of the fractures are within this range. They are close to the monitoring well, so we could say that the PKN made reasonable predictions. The ones that are too short or too long are indicators that something unexpected happened at that stage. If it's too short, we could say that the fracture was already there as it propagated very fast. And if it's too long, the cluster might have failed and the liquid might have traveled along the well until it found a fracture to propagate through, as it took it a long time to reach the monitoring well. We also plotted the microseismic cloud length next to the Pekian fracture half-lengths to compare. We can see how fractures are longer in the early stages than in later ones. And like I said, this is mostly because the time of ejection is longer in these early stages. Mostly the Pekian fractures are larger than the microseismic ones, and this could be because, well, the model does not consider leak-off, fracture toughness, or stress changes. But we can see how the fractures are agreeing with each other. However, in the middle, they are not at all. The difference between the Pekian fractures and the microseismic length is bigger than in any other stages. And we want to look back at what happened in these stages. After all these analyses were done, we compile a list of the expected characteristics displaying the different observations to make the analysis of each stage easier. These characteristics are a noticeable heart-shaped tip, a nice formation breakdown pressure, a lack of the antenna signal, azimuths with perpendicular propagation. The fracture growth is reasonably described by the Pekian model, meaning the dust heat fractures are close to the monitoring well. The Pekian fracture and the microseismic cloud have similar length and trajectory. And finally, the microseismicity overlays on top of the fracture strain signal. In-depth analysis is being conducted for all the stages, especially focused on complex cases, to find properties and other characteristics of failed stages. From preliminary results of this integrated analysis, we have found the characteristics of a stage that presents an already existing fracture, which are the absence of the heart-shaped tip in the dust stream front, lack of formation breakdown pressure peak, and the dust heat fracture half-length is very short. If a stage presents these characteristics, we can say that the fracture in the stream front was a persistent fracture. We also found that the fractures that propagated with an inclination could have two explanations, and we can determine which one it is by observing the fracture half-length at the dust heat. If the dust heat is very long, that means that the fracture took longer than expected to propagate, which could mean the cluster failed to create a fracture and the fluid propagated along the well until it found a fracture to move through, which explains why the frac azimuth is not perpendicular. However, if the dust heat length is within the range of good agreement, that means the fracture took the expected time to arrive to the monitoring well, which could mean the deviation is because there are other fractures or weakness planes in the formation that diverted the fracture. Now, to wrap this up, comparing dust pumping information and microseismicity reveals a lot of information on fracture propagation speed, length, and trajectory, especially when compared with a simple model like PKN. The expected characteristics for this analysis are a heart-shaped tip, a formation breakdown pressure, lack of antenna, perpendicular azimuth, microseismicity on top of dragonfly, and the Pekian gives reasonable parts. At this stage of the analysis, we have found that the absence of heart-shaped tip means that the fracture was already open, that antennas come from openings in previous stages, and that we can determine whether the fracture propagated with an inclination due to normal deviation in the formation or to the cluster failing to create a fracture. We hope to find that different data types reveal or does not reveal. I have for well with dozens of stages to look at, so there is still a lot of information that we can get, so keep in tune. I would like to thank the sponsors of the Microseismic Consortium for financial support and the anonymous company that gave us permission to use and display the data. And that is all for now. Thank you very much for your time.